All right. Hello, everyone. So today is the lecture number 2, and here is the brief recall of what we've done last time, right? So last time we introduced this concept of linear vector space, and so we discussed how we introduce this type of space. So basically it's defined by these two operations of vector addition and scalar multiplication of a vector by a scalar, a constant, right? Then we introduce this important concept of linear independence of vectors, and through this concept we introduce the thing of dimensionality of space, the space dimension. Then we introduce the concept of the basis in any arbitrary linear space, and the way how we represent a vector through the combinations of the vector basis vectors E, in this case E, times the projection of the corresponding vector on the vector basis, right? Then again, I remind you that sometimes when we meet the index that we use to, for summation, like in this case, we will usually omit the summation index, summation symbol, and then we started discussing the different products of the vectors, and we discussed, as far as I remember, we discussed this inner product, also known as dot product, and scalar product of two vectors. So if you have two vectors, the dot product is an operation that allows you to get the scalar as a result. And in particular, this operation allows us to find the absolute value or the size of the vector through this operation. Right, so this is what we discussed last time, and today we proceed with the different vector operations, and the first one that we that I remind you is cross product. Cross product. So we won't use much this product in this quantum course, but for the sake of completeness, I also want to discuss it here. So the cross product is denoted by this cross between two vectors, right? Or sometimes in the textbooks you can find this notation of two vectors with the in the rectangular brackets with the comma between. Right, so this is basically the same. And the way how we find the cross product of two vectors is through determinant of a matrix. Right, determinant of the matrix composed of the basis vectors E1, E2, E3. So we choose the basis, and then the second row is components of the first vector A1, A2, A3, and the third row is the components of the last vector B1, B2, B3. I guess some I mean, some problems in your first homework. You will need this for your homework, right? So note that in contrast to the scalar product, in this case, as a result is a vector, is another vector, a vector, and this vector is orthogonal to both vectors A and B. To A and B. Orthogonal means rectangular, right? Or hi. Give me a second. Yeah, so the result is another vector orthogonal to vectors A and B. So how we obtain the determinant of any rectangular matrix, right? So I just remind you that the determinant of 2 by 2 matrix, like any 2 by 2 matrix with components C11, C12, C21, C22, is equal to the product of diagonal components minus the product of the off-diagonal components, right? So it is equal to C11, C22 minus C12 times C21. So this is the result for a matrix 2 by 2, but in the case of like a larger matrix of 3 by 3 with elements C11, C12, C13, C21, C22, C23, C31, C32, C33. We can represent it as a, I mean, through the minor representation, right? Minor decomposition. So how we do that? Just remind you. So we can select any row or column, and I mean, traditionally we use the first row, and for the first element in this row, which is the element 1, 1, we cross out the corresponding row and column. And as a result, we obtain this submatrix C22, C23, C32, C33. So this is called minor, right? So for the determinant, we write this element C11 with the sign of so how we define the sign of this element? So for the corresponding element with indices 1 and 1, right? The sum of these two gives is equal to 2, and 2 is even number, so we put plus before this corresponding element C11, and then we write this determinant for this submatrix for the minor C22, C23, C32, C33. Double vertical line is another way we denote the determinant. Then for the second element, which is C12, 1 plus 2 gives us 3, 3 is odd, so we put minus. Then this element C11, and another minor, which is C21, C23, C31, and C33. And finally, for the last element in the row, which is C13. 1 plus 3 is even, it's 4. So let's put plus 1, 3, and the corresponding minor, which is C12, C22, C31, and C32. And then each of these determinants of the minors, you can use the formula above to represent this as a final formula for the determinant. And since the first row in this determinant is the corresponding basis vectors, so the result will be also vectors. For example, for the vectors A and B introduced above, right, with this determinant, we write the final formula E1 then times the corresponding minor A2 B3 minus A3 B2, then plus E2 vector A3 B1 minus A1 B3, then plus E3 A1 B2 minus A2 B1. So this is about cross product. As a result, we get the another vector orthogonal to the vectors A and B. So the next product is tensor product, and we also will discuss this dyadic product. So so this type of product is very frequently meet in the quantum theory, and in quantum computing we're gonna use this quite a lot. So the tensor product, let's maybe even highlight this one. Okay, dyadic product. The result of this is matrix. The result is a, let's write vector slash matrix, because the tensor product creates vector, dyadic product creates matrix. So the way how we denote a tensor vector, a tensor product, is this little circle with the cross inside. And for two vectors A and B, right, if we represent these vectors by their components, vector A1, A2, for example, we consider two-dimensional space, the simplest case, right? The tensor product, vector B with components B1 and B2. The tensor product is the operation when we multiply the components of the first vector by the second vector itself. So, for example, for the first one, we get A1 element times the second vector B1, B2, and for the same for the second component A2, B1, B2. So it's a vector of vectors. So it looks like this. And if we expand this further, we multiply the component A1 by each of the components of the vector B. So in the result, we get another vector with components A1, B1, A1, B2. So this is this part of the product, and then A2, B1, A2, B2, right? So in the input, we had two-dimensional vectors. In the output, we get one vector, which is four-dimensional. So a vector with four components. We can actually denote it. 2D vector, and in the output, we get 4D vector, four-dimensional vector. Four-dimensional vector. The same way we can define the tensor product of two matrices, not only vectors but also matrices. For example, for two matrices A and B with components A1, A2, A3, A4, we can multiply this matrix by another matrix B1, B2, B3, B4, right? And as a result, I mean, operation is exactly the same as with the vectors. So in result, we get a matrix. When we multiply, where we multiply each component of the first matrix by the second matrix. So it looks like the first component multiplied by B1, B2, B3, B4, right? Then the second component, again, multiplied by matrix B. Let me denote it by like this, the matrix B. And then third component by matrix B. And the fourth component also multiplied by the entire matrix B. So in the result, we can rewrite this as a bigger matrix with the elements A1, B1, A1, B2, A1, B3, A1, B4, the first submatrix. Next, A2, B1, A2, B2, A2, B3, A2, B4. Then next, A3, B1, A3, B2, A3, B3, A3, B4, and finally A4, B1, A4, B2, A4, B3, A4, B4. Yeah, such a big, large new matrix. So in the input, we had two by two matrices. In the output, we get one 4 by 4 matrix, right? So here in the quantum computing, there is a one, useful notation for vector and matrices. So let me write this in color. Useful notation. So one can meet something like a vector to the power of tensor product n. Or for the matrix, one can find also something like this. So this power of tensor product to the power of n, right? So basically tensor product of n times. And that basically means that for any vector like this 1, 0, right? It's a type of vector and actually pretty important one. So the something like tensor 1 would denote basically the same as this vector 1, 0. Yes?
I'm so sorry. What letter is that next to the A?
You mean this one? M. Sorry, M.
Yeah, thanks.
Matrix. matrix. Yeah, so basically a vector column to the power of tensor 1 means we take the tensor product. I mean, we take the vector itself without making the product. But for the same vector 1, 0, tensor 2, it means that we take this vector and tensor multiply this by itself, right? So when you do that, what you get is 1 by 1 gives 1, 1 by 0, 0, and then 0 by all these elements of the second vector is 0. So this is a new vector 1 and then 000. And the same way it can be expanded to tensor 3 to the power 3, 4, etc. And for a matrix like 0, 1, 1, 0, it's another type of like pretty useful matrix. Again, this tensor 1 gives the matrix itself 0, 1, 1, 0. But for the tensor product of the power of 2, it's the matrix by matrix, which is so for the first one, because of the 0, it is all zeros, right? Then for the 1, I get it, this matrix itself. Then for the 1, again, matrix itself. And then for 0, all zeros. Something like this. Yeah. So I think we will use this notation throughout the course. So this is about vectors, vector space, and vector products. And I suggest that we describe an example. As an example, we take the Euclidean space. Euclidean space. So what is Euclidean space? Euclidean space is the space where we live. That's our space, right? Three-dimensional Euclidean space. So how we describe this space? We describe this introducing a coordinate system x, y, and z. X, y, and z. Right. So we often introduce these unit vectors, which are basis vectors. We denote them I, j, and k. Right. So these are unit vectors that form the basis for our space. So this space is three-dimensional. I, j, k are linearly independent. That's why we can use these unit vectors as the basis for our space, right? And since we introduce this coordinate system, we can take any vector in this space. And again, the vector itself doesn't depend on the choice of the coordinate system, but its components do. So when you rotate the coordinate system, the components of this vector will also change. For example, a x component is given by the absolute value of the vector itself by cosine of the function, of the vector of this lambda. Lambda is the angle between the axis x and the vector itself. And the same way for the component y, it is I cosine beta. Beta is the angle between y axis and the vector. And the final one, AZ, is given by the absolute value of the vector or its length. And cosine gamma. Gamma is the vector, is the angle between the vector and the axis z. Right? So these components, a, x, a, y, and z, they of course depends on the rotation of the coordinate system because of these cosines, cosine alpha, beta, gamma. You rotate the coordinate system, you change the angles, the resulting components also do change. But if you take the square of these expressions and then sum them up, right? Cosine squared plus cosine squared plus cosine squared will give you basically 1. And as a result, a square would be equal to ax squared plus ay squared plus az squared, or the length of the vector is given by this formula that we already discussed. And and this expression, this formula, doesn't depend on the choice of the coordinate system. For any two vectors in this space, like for the vector A and for vector B, we can write the dot product. It will be given by the product of the corresponding components, ax bx plus ay by plus az bz, right? For the cross component, we also can use this this formula above that we this one that we discussed today. I know a trick how to remember this formula. So for any cross product like this in our xyz coordinate system, we first write the unit vector for the x, and then in the parentheses we put the, so this is x, then I put the y component of a, y, and then z component of b, and then minus basically the same, but I flip the components a, z, b, y. This is so x, y, z, but then zy, and then it works the same for all the terms. So then it comes j, right? So j corresponds to y, so it's y. Then I put the first one is z, then bx, then minus ax bz, and finally plus the last one, the unit vector along z direction, z, that means that the first one is x, then y minus y bx, something like this. So it's a circular substitution of x, y, and z, from x to y, from y to z, from z to x, something like this. So it's very easy to remember even a formula like this, right? Then for these two vectors, we can of course write the tensor product. So it's a product of ax, ay, az, tensor product bx, by, bz, right? And it's gonna be very large vector with components, 9 components, right? So it's gonna be ax, bx, ax, by, ax, bz, ay, bx, ay, by, ay, bz, AZBX, AZBY, AZBZ. Okay. So in quantum, we are not going to use such a, I mean, at least analytically or theoretically, we are not going to use this big vector. So usually our vectors will be either two-dimensional, and two-dimensional vector will correspond to this qubit, the state of a qubit, right? And then tensor products of two-dimensional qubits, which are four-dimensional, etc. And what else did I didn't discuss the dyadic product, but okay, the dyadic product is pretty straightforward. It's basically also tensor product. Let me exemplify this. So for this vector b, bx, by, bz column, right? If I transpose this vector b, so the transposed vector is basically a row of the same components. So it will be bx, by, bz, right? So this is the column of the same components, transposed vector b. And if I take the tensor product of the vector a, tensor product b transposed, let's see what I get, right? Basically, what I write the column of ax, ay, az, and then tensor. And for the transposed vector b, I write the row bx, by, bz, right? So the product of column by row, how we do that? We basically, I mean, according to the matrix product rules, right? We take the product of elements in the row in the first matrix or vector by the elements of the column in the second vector or tensor. So for in this case, we have only one element in the row in the first vector, so it's ax, and I multiply this by bx. Then for the second, I take ax, multiply by the second one, by, and for lastly for ax, bz, right? And obviously the other elements will be ay, bx, ay, by, ay, bz, az, bx, az, by, az, bz matrix. Yeah. So in contrast to the tensor product, when we had two vectors and a result is another vector, the product of the dyadic product. So this is dyadic product. So dyadic product takes two vectors and it creates a matrix. It creates a matrix. All right. So this is about the vectors in the arbitrarily linear space. And now we can proceed with the next topic. Let me put lecture number 2, because that was actually the plan for the first lecture, and this is the topic for the second one. So lecture number 2, complex numbers and complex functions. And we will start discussing matrix operations. Matrix operations. And I will assign another homework. So it will be homework number 2 about complex numbers and matrix operations. Your first homework also contains some problems with complex numbers. So this part is also useful for you. And actually, the whole quantum mechanics, quantum computing is based on the vectors and matrices of complex valued elements, complex valued numbers and functions. So this is also must know. So let me remind you the way how we introduce the real numbers, right? Real numbers, we can basically put them on an axis of numbers. So let me call this axis of real numbers. Real numbers, we will denote it by x. So this x denotes the axis of real numbers. On this axis, we of course have 0. We have some 1, right? Like integer numbers, positive integer numbers, negative integer numbers, and of course we have other numbers like rational, irrational numbers, 0.5, etc. So basically all the real numbers are can be placed on this axis, right? And but very often in engineering and especially in quantum, it's not enough to have these only real numbers. We need to introduce the imaginary part of numbers, and we do that by continuing these to the complex plane. So we still have all these real numbers on the real number axis, but we also introduce the orthogonal axis of imaginary numbers, and we will denote it by axis y. So the imaginary numbers are a little bit different. For example, the unit in the imaginary numbers axis is named I, and the second element is 2i, and etc. 3i, 4i, 10i, 100, 1000i, etc. And also, in the negative, it gets minus i, minus 2i, and etc. Right, so this is imaginary numbers. What is I here? So the I introduced as the square root of minus 1. So that if I take if I take I times I, or I to the power of 2, it's equal to minus 1. Right, this is something unusual that we are not used to. When you take any number to the, if you take square of any number, you're supposed to get the positive number, but in this case we get a negative number, so it's a little bit unusual, and some students have problems with understanding these numbers, and like why we need these numbers if we don't meet them in actual life, right? So why we introduce these numbers? But if you think a little bit about, for example, negative numbers, you will also recognize that, or acknowledge that you also don't meet negative numbers in real life, unless you do some some bank operations, right? Like you can get minus on your bank account, but that's also something that you cannot meet in real life. Negative numbers, they were introduced into the math to be able to do this bank operations. When you owe something to another person, you can say that you have minus something, right? Like minus amount of money. And then of course, scientists observed the two different type of charges, electric positive and negative. So this type of math of negative numbers became very useful for physics, because since we have this math, we can build the theory of electromagnetism, which deals with two different opposite charges, positive or negative. And the same way here with the imaginary numbers. At some point we realized that it's not enough to have only real numbers, positive or negative, and we need to bring another numbers, and these numbers are called complex numbers. So the complex number is the composition of both of real and imaginary number. And these numbers, complex numbers, they denoted by points in this complex number plane, right? So this dot, this point, I can write something like z, which is complex number, and it's equal to I plus iy. So it's basically the sum of a real number and imaginary number. And by the way, there is yet another class of numbers. You probably heard of them. They called quaternions, right? So it's another. It's a continuation of this of this concept of imaginary numbers to four-dimensional space. And these quaternions are widely used by like engineers, people who describe how the object is oriented in space. For example, people who design like planes, they use these quaternions quite a lot. So so the imaginary numbers is not the final type of numbers. We need like generalization of them to the larger dimensions, to quaternions, and maybe so on. So the complex number z is the composition, is the sum of real part x plus I times y. Y is the imaginary number, imaginary part of this complex number. So this point in the complex plane can be given by the distance from the origin of this complex number axis, plane, and it can be given by the distance from the origin. So it's a modulus z, right? And by the rotation angle phi, was denoted by phi. So how we can define this phi? For example, we can take the cosine of this phi, right? So cosine of angle phi, what it is? It is the leg x, right? Leg x in this right rectangle triangle. So it's a x, and then over the hypotenuse, which is modulus z in this case, right? And the same way for sine phi, we get y leg over hypotenuse z, or modulus z. So from here, we get for x is equal to modulus z times cosine phi. From here, we get y modulus z sine phi, right? And for the complex number z, which is x plus I, y, we substitute x and y by these formulas, and we get modulus z, and in parentheses, we get cosine phi plus I sine phi. So let me rewrite this here. Z equals modulus z cosine phi plus I sine phi. So this is the sine cosine representation of the complex number. So what is left undefined here is the angle, right? So to define the angle, I can, for example, divide this expression for sine by expression for the cosine. So my modulus z cancel out, and I get for the tangential phi, right? I get what? I get y over x. I get y over x. Hence, the phi is arc tang y over x. So this is the formula for y. Like if you have the real and imaginary number of a complex number, you can divide them, take arc tangent of this ratio, and that will give you the angle phi. So why I'm writing in blue, let's change color to black. So for a given complex number, z equals x plus iy, I can write the complex conjugated counterpart, which is denoted by this star, right? So the z star is the complex conjugated number, which is the same x, the same y, but the minus, I mean, the sign before this I is changed to minus. So basically x minus I, x minus iy. So this is complex conjugated. Complex conjugated number, the complex conjugated counterpart to the number. So why we need this complex conjugated number to do, I mean, to figure out that, let's take the product of the two. Z times Z conjugated. What we get? We get x plus iy times x minus iy, right? And it's equal to the square of the first one and minus the square of the second one, right? So it's equal to x squared plus y squared, because the square of I gives you -1, and this minus with -1 gives you plus. So yeah, you get x squared plus y squared. In the same time, if you take the square of these formulas 1 and 2 over here, what you get? You get cosine square phi equals to x square z modulus square. And for the sine, the same, sine squared phi is equal to y squared over z squared. And now if you take the sum of the two, you get cosine square plus sine square, which gives you 1. Cosine square phi plus sine square phi is equal to 1 for any angle phi, right? And what you get? You get x squared over z squared plus y squared over modulus z squared is equal to 1. So you multiply by modulus z squared, both parts, and you get x squared plus y squared equals to modulus z squared. Modulus z squared. And now, if you compare this one and this line and that line, you conclude that z times z conjugated is equal to modulus z squared. So the product, let me actually frame this in red. So the product of complex number and the complex conjugated number of the same number gives the absolute value squared of the complex number. And according to this formula, the absolute value of complex number is the real number. X squared plus y squared, of course, is real. Is a real number. So what would we get if we take the sum of the two, of complex number plus the conjugate counterpart of the same number, right? So in this case we get 2x because iy and minus iy cancel out. We get 2x, which means that if we divide by 2 both parts, we get for x, we get z plus z star over 2. So this is the real part of complex number z. So if you have a complex number, you can take the the conjugation of this complex number, take the sum of the two, divide by 2, and this way you get the real part of complex number. So x is nothing but real part of complex number. All right, and the same way, if you take the minus, if you subtract the conjugated from the same, from the complex number, you get 2iy. That means that y is equal to z minus z star over 2i, and y, of course, is imaginary part of complex number. So at this moment we need to introduce a very very important formula which bears the name of like famous mathematician Euler, right? Euler's formula. And I even write the name of this formula in red because I believe this is one of the most important formulas in the entire engineering area. So this formula states that e to the power of I phi is the angle, right? I is the imaginary unit, is equal to cosine this phi plus I sine the phi. So this is the Euler's formula. In order to prove this formula, we need to tailor, or basically to represent cosine and sine as a series by the power, right? And then compare it with the same series for the exponential function. So we don't gonna do that now, but here is the formula, and the formula is very very important for the I mean, for the quantum, of course, and for the engineering. So first of all, for example, if we take something like e to the power of I0, so 0, the angle is 0. What would we get? It means that we need to take the cosine 0 plus I sine 0. You know that the sine 0 is 0, cosine 0 is 1, so it's equal to 1. So e to the power of I0 is equal to 1. Likewise, if you take e to the power of I and some angle like pi over 2, very good number, pi over 2, you substitute for pi over 2 for pi or for phi angle. For the cosine you get 0, for the sine you get 1, so you get the imaginary unit. Something like something like this. And yeah, and let's figure out what would we get if we take the complex conjugation of this e to the power of I phi. So we can represent this e to the power of I phi as the cosine phi, real number, plus I sine phi, another real number, complex conjugation. So in order to get the complex conjugation, complex conjugated number, we change the sign before I, so we get cosine phi minus I sine phi, and this is nothing but e to the power of minus I phi, right? So that means that when we take the complex conjugation of the exponential function like this, we also can just change the sign of the complex of the imaginary unit, and that will give you the complex conjugation. So, but we know that the product of complex number E phi by the complex conjugation of the same number minus E phi supposed to give us the length, right? The value, the absolute value of the corresponding complex number. In this case, because of this rule of product of two exponential function, we get e to the power of I phi minus I phi, which is e to the power of 0, which is 1. So we conclude that e to the power of I phi is the complex number with the length of 1. Is the length of 1. At the same time, if we take the sum of the two, right, e to the power of I phi plus e to the power of minus I phi, what would we get from this formula, from the Euler's formula? It's equal to 2 cosine phi, which means that any cosine function, like quite often we represent a voltage or current or the field strength, right, as a function of sine and cosine. So the cosine function can be represented as the sum of the two exponential functions, e to the power of I phi plus e to the power of I minus I phi over 2. This is pretty important formula. And at the same time, if we take this the subtraction, the minus here, we will get 2i sine function. So we get the final result, sine any function, any angle phi is equal to e to the power of I phi minus e to the power of minus I phi over 2i. So again, we can represent any sinusoidal function as a composition of two exponential functions. Pretty good. And let's return to the sine cosine representation of complex number. So it was modulus this number, right? Then times cosine some angle phi plus I sine this angle phi. According to the Euler's formula, this equals to e to the power of I phi. E to the power of I phi. And we conclude that we can rewrite this sine cosine representation of complex number in this way. And this representation, let me actually summarize the three ways we can write the complex number. So first of all, any complex number can be written as a composition of, or as a sum of real number. Oh, it was x, I believe, right? It was x plus I y. So this is the real and imaginary number representation of complex number, xy representation. Then the second one was modulus z times cosine phi plus e and is I sine phi. I sine phi. So this is sine cosine representation. And finally, we have another one to the power of I phi. So this is exponential form of complex number. Exponential form of complex number. Exponential form of complex number. So why all this important? So all this is important because in quantum mechanics, quantum theory, quantum computing, the vectors and matrices are complex numbers, are complex valued. So in quantum, we represent the states of quantum system as a complex valued vector. And we will, of course, discuss that in a while. And any operations with those vectors are given by matrices, and they are complex valued matrices. All right, so I think we can describe a couple of problems, couple of examples. So let's write problems in blue. So the problem number one. Let's find the absolute value of one simple vector. So absolute value of vector v with components 1 and I. So I specifically consider the complex valued vector because, as I believe in your homework, you have these complex vectors. So it's going to be a good practice for you before you accomplish your homework. So absolute value of this vector, and on top of that, let's also normalize the vector. Normalize the vector. It means that bring the length of the vector to 1. So the only direction of the vector matters, but the length of the vector is equal to 1. How we do so? I mean, obviously we need to divide the components of the vector by the absolute value, by the length of this vector. And in result, we get the vector of unit length. So absolute value of this vector v, 1 and I. Right. To do so, we need to so first of all, this vector is complex valued, and for the length, for the absolute value of this vector, we need to find the complex conjugated vector v, which is 1 and minus I, right? We just change the sign of the imaginary unit. So we get minus I here. So for the absolute value squared of this vector, we need to multiply this vector by the complex conjugated vector. Complex conjugated vector. So we write for the first one is 1I, but the second one, I mean, if we want to follow the rules of the matrix product, we have to also take the transposition of the second vector, right? So I write the same but complex conjugated, and of course I know that the dot product of two vectors is the sum of the product of corresponding components, but we're gonna use this matrix product quite a lot, so I put T here, the transposed. So it's gonna be 1I for the first one, and the second one is transposed, so it 1 minus I, like this, right? So after that, I can use this matrix product rule when I take the first component of the first vector, and then it times the first component of the second vector, and the same for another component. So it's 1 times 1 plus minus I times I is equal to 1 plus minus, and I times I gives me minus 1, so it's another 1, so it's equal to 2. So the absolute value squared is 2. The absolute value itself is square root of 2, right? And so this is the answer to the first line, to the first question. And the second one is normalize the vector. So in order to normalize the vector, I have to divide each component of this vector by its length. So it's gonna be 1 over square root of 2 and I over square root of 2. Pretty good. And of course I can write this 1 over square root of 2 before the vector itself, 1 I. Yeah, so this vector is normalized. If you calculate the absolute value of this vector, you will get 1. This normalization is also very important for quantum theory. We will discuss it in what follows. So the problem 2. Let's take something very, very simple. So let's, using this Euler's formula, let's express e to the power of I pi over 3 in the xy form. In the xy form. So we use the Euler's formula, e to the power of I phi, it's equal to cosine phi plus I sine phi, right? So we just need to substitute the pi over 3 for pi over 3 for phi. So it's a cosine pi over 3 plus I sine pi over 3. Sorry for my handwriting. So cosine pi over 3, as far as I remember, that's 1/2, right? Plus I, it's a square root of 3 over 2 for the sine. Yeah. And so this is basically the representation x plus I y. This is x, this is y, this is unit, imaginary unit. Yeah, so this is how it works. Let's consider yet another problem, problem 3, and find, for example, the absolute value and the angle phi of simple complex number. Let's take 3 minus 4i, something like this. So we need to find the absolute value of z and an angle phi. So the absolute value squared of any complex number is the square root of real part plus square root of the square of real part plus square of imaginary part. So real part here is 3 to the power of 2 is 9. Y is equal to minus 4. Square gives us 16. So the answer is 25. And the modulus, the absolute value is square root of it, so it's 5. Right. So it's 5. And for the phi, we recall this formula arc tangents. So what we get? We get minus 4 for y, minus 4 over real part, over 3. Okay, so or it's equal to minus arctangents 4 over 3, arctangent 4 over 3. And this is of course some angle. And yeah, let's consider another problem. Problem 4. Simple one. Let's evaluate something like 1 minus I divided by 1 plus I. Right. Evaluate this. So in order to do something like, this expression, we need to get rid of the complex number and unit and imaginary unit in the denominator. The easiest way to do so is to multiply by the complex conjugated denominator, right? Because when we take the product of complex number and complex conjugated number, we get real number. But we need also to multiply the numerator by the same to keep the, to keep it correct. So for 1 minus I times 1 minus I is equal to 1 minus I squared. And the denominator is obviously 1 plus 1, which is equal to, right? So it's a absolute value of 1 minus I number. So it's 2. For the numerator, we get 1, then minus 2i, then plus I squared. I squared gives me minus 1 over 2. 1 minus 1 is equal to 0. So I get minus 2i over 2 is equal to minus I. Right. So I'm just remind you how this works. So the problem number 5. Problem number 5. This one is curious. So what is what is I to the power of 2023? Right. So this is the year. This is our year. What is I to the power of 2023? So to figure out that, we can first consider the I to the power of 1, which is just 1, right? Obviously, this is just I. Then I to the power of 2 is minus 1, as we just figured out. I to the power of 3 is equal to minus I. I to the power of 4 is equal to 1. Is equal to 1 because it is minus I times I gives us 1. And then I to the power of 5 is I again. And then I to the power of 6 is minus 1. I to the power of 7 is minus I, etc. So it's a periodic operation. So we can write this something like repeating every first step. Every first step we get 1, right? We get 1. That means that if we divide 2023 by 4 and take the remainder of this operation, let me divide this 2023 divided by 4 and then remainder. So I get 3. So the 3 is the remainder. That means that all these other 2020 operations I just can skip because it's periodic operation. So I just skip the 2020 operations, and the third operation in this from this column is minus I. So I to the power of 2023 is the same as I to the power of 3, just 3, and is equals to minus I. Yeah, so this is how we basically work with the powers of complex numbers and imaginary union in particular. So now I need to introduce a pretty important concept of Dirac notation. So the Dirac notation for vectors. Dirac notation for vectors. So in quantum realm, instead of denoting vectors by rows or by arrows on top, we use this Dirac notation. Dirac notation of ket and bra vectors. In this notation, the ket vector is denoted by this. So V stands for the name of the vector, and then I place this name of the vector between vertical line and this angular bracket, right? So this is bracket ket vector, and the ket vector denotes a vector column, and in 2 dimension it would be something like AB vector. but of course the vector can be three-dimensional. For example, for another vector like this psi vector, I can write something like A, B, C vector, and etc. So this is cat vector. Cat vector. So let us make a small, sorry for the little break. Yeah, but I had to change my AirPods. All right, so Dirac notation. In Dirac notation, we use this cat vector, which is denoted by this vertical line and this angular bracket, right? And this is yet another way we denote a vector. And why is this? Why is this name cat? Because in pair with the cat vector, we introduce another, the counterpart, the bra vector. And the way we do that is, first of all, if we take the complex conjugation of this vector, we just need to complex conjugate the corresponding components of the vector. That's clear. But if I take the complex conjugation and transpose of the cat vector, I get the counterpart, the bra vector of this vector v. So that if I take, for example, if I calculate the absolute value squared of my vector v, how I do so? By definition, since this vector is complex, right, I write v times v complex conjugated, and the same, the same operation I can write in the Dirac notation as the bra vector times cat vector. Bra times cat, or bra cat. Instead of writing this line, then dot, another line, we simply substitute that by just one line. So it's the same as v vector times v. So bra cat. So this one is bra, this one is cat. Altogether it says bracket or bracket. That's why, hence the name. Let's write this somewhere here. So this is cat vector. The counterpart, the transposed and complex conjugated, is the bra vector, and the composition like this is bracket composition. And now, obviously, this bracket is scalar, complex valued. Oh no, this is just scalar, real valued scalar bracket. And of course, if I say I have one vector cat, but another vector bra, I can of course write something like BA, right? So this is the bracket composition of two different vectors. And of course, if I have a cat, I can write the corresponding bra vector, and the same for B. For the bra B, I can write a cat, so I can also write something like A times B. That's also possible for any two different, I mean, for any two vectors. It can be different, can be the same. Let's consider, I guess, one or two examples. So the example. So for the example, let's take the most important and at the same time the easiest vectors we have in quantum. We denote this vector 0. The vector 0 gets components 1 and 0, like this, and vector 1. And the vector 1 gets components 0, 1. So this is the column representation of the two. And of course, for the vector 0, for the cat, I can write the vector bra. 0 and 1 are real valued, so complex conjugation don't change them. And what I need to do, I just need to take the transposition of the vector. So I get 1, 0. And the same for the, bra, I can write bra vector for the vector 1. It's equal to 0, 1. Pretty easy, right? So let's calculate the bracket 1, 0. What would I get? So bra vector comes first, and for the bra I need to, I need the transpose the bra, right? So I write 0, 1, this vector, and then times cat. Cat is the column. So I write 1, 0, right? So taking the product, 0 times 1 is 0, 1 times 0 is 1 is 0, so I get 0. I get 0. And let's consider the opposite, the 0 times 1 bracket, composition of 0. So now the 0 is bra, so I write 1, 0, and cat is column is 1, so it is 0, 1. And again, 1 times 0 is 0, 0 times 1 is 0, so I get 0. It's interesting because 0 and 1, when I take the product of the two, the inner product or dot product, I get 0. That simply means that the vectors, they are orthogonal, orthogonal vectors. And since they are orthogonal, two-dimensional vectors, so I found two linearly independent orthogonal vectors in the two-dimensional space. That means that I can use these two vectors, 0 and 1, as the basis in the corresponding two-dimensional space. So we will use that quite a lot in what follows. But yeah, let's consider another example. Example 2. And as an example, and this actually also a pretty important composition is, so we considered bracket composition of two vectors, but we can of course consider the reversed case of cat bra composition, or cat bra product, or something like for the cat, right? Something like this times for the bra, something like this. So what is this in that case? So I write my cat 0 times my bra 1. And again, so for these two brackets and the dot between, we use the shortcut version of, or shorthand version of this writing, which is 0, and then I write these two brackets just by this x, so something like this. So I put x and then 1. So this is the same as the first term. So we can use the rules of matrix products to find what is this cat-bra construct, right? So for the 0 state, and this is cat, so it's a column. For the column 0, I get 1, 0, and then times for the bra 1, I get 0, 1. So now I have the first vector is column, the second is row. So again, I have to multiply 1 by the first element, but I have only one component, basically only one component in the row of the first element. So I have to write 1 times 0, which is 0, and that's it. So this is the first component in this operation. And then for the second component, I have to write 1 times 1, which is 1. And then again for the second row, which is 0 times 0, 0 times 1. So it's a 0, 0. So you see, as a result of cat-bra product, instead of scalar or vector, I get a matrix, 2 by 2, 2 by 2 matrix with 2 rows and 2 columns, rows and 2 columns. So yeah, the result of this operation, of this cat-bra operation, is a matrix. The result of the bracket operation is a scalar. And this is quite important for for what follows. And this also brings us to the importance of matrices in quantum field. So the next topic, and we're gonna just start it today and continue next week, is matrices and matrix operations. Matrices and matrix operations. Important topic. So generally speaking, a matrix, and by the way, we are mostly interested in the square matrices, when the elements, the number of columns is equal to the number of rows. So the any square matrix of n dimension, in n dimension, can be written as C with indices A and J, where I stands for, or corresponds to, denotes the rows, and J denotes the columns. So it can be written as this matrix of elements C11, C12, etc., C1n, if the space is n dimension. Then for the second one is 2, 1, 2, 2, 2n, and all the way to Cn1, Cn2, Cnn, if the matrix is quadratic or squared. So this is the matrix, right? And so first of all, for the matrix, we already know this operation of determinant. So we can take a determinant of this matrix, and we also denoted by this double line ij, something like this. This is also determinant. So we already know that this determinant is given by the minor representation through minors. So it's basically the sum over some raw elements in one row, And then we have this -1 I plus j. Again, if I plus j is even, it is plus. If I plus j is odd, it's minus. And times minors, right? Ij. So this is the determinant, or minor representation of the determinant. And again, I repeat that determinant, why it's important, it represents the thing that doesn't change upon transformation of coordinate system. So it's an invariant of the matrix. So the next operation we also already mentioned it is transposition. Transpose, right? So how we do transpose? We simply replace row by columns and columns by rows. So if for the matrix Cij, I gives the rows, j stands for the columns. If I take the transposition, I simply exchange the rows and columns. And by the way, sometimes it's also written with this wavy line on top. So it's the same, basically the same thing. J, I. So I swap the indices. First it was ij, so now it's ji. So basically I took my matrix and rotate, right? So I have a matrix like this with some elements over there. I have the, the quadratic matrix gets this main diagonal. And the way how we do transpose, we simply rotate this matrix over this diagonal like this. So the column becomes row, the row becomes column. So this is the transposition. So the next operation is complex conjugation. Complex conjugation. This is very simple. The complex conjugation of any matrix is just the same matrix of complex conjugated components. Complex conjugated components. But this brings us to very important concept for the next. It's called Hermitian conjugate. Hermitian conjugate. So what is Hermitian conjugate? So by the way, it's denoted by dagger. This C dagger. It's, we named this dagger. It looks like the little plus, but when you read, especially old books on quantum, this sign was like a small dagger. So that's why we call this dagger C dagger. And if this Hermitian conjugate, if I do this Hermitian conjugation, I apply this dagger to the matrix. What basically I do, I complex conjugate all the components in the matrix, and I transpose the matrix. So it's a complex conjugation and ji. This is the definition of Hermitian conjugation. Hermitian conjugate. Let's frame this in red. Hermitian conjugation. Some matrices don't change when you, after application of Hermitian conjugation. And And these matrices that don't change after Hermitian conjugation are named Hermitian matrix. So let me write this in red. So a matrix is Hermitian. A matrix is Hermitian if C dagger equals C, or Cij equals to Cij. And this type of matrix is Hermitian matrix. A simple example. Let's write this examples. Right, example. So a simple example or trivial one would be something like 1, 2, 2, 3, something like this. So you complex conjugate, but these are real numbers. They don't change. And when you transpose, so again you rotate this matrix around the main diagonal. So 2 becomes 2, and so nothing changes, right? So this matrix after Hermitian conjugation becomes 1, 2, 2, 3. Okay, but this is trivial. Something more, untrivial example would be something like 1, then 1 plus 2i, 1 minus 2i, and here's 2, for example. Oops, this is matrix, not determinant, the matrix. So let's take the Hermitian conjugation. So we need to Hermitially conjugate, we need to complex conjugate the matrix. It's pretty easy to see. So when we complex conjugate, this becomes minus here, this becomes plus, right? But after transposition, they exchange, so I get exactly the same matrix. I get exactly the same. 1 plus 2i, 1 minus 2i, and 2. You see, so this, and one can figure out many matrices like this, I mean, or even more interesting matrices that also don't change after Hermitian conjugation. So this matrix is Hermitian matrix. And the importance of these Hermitian matrices is that they represent all physical quantities in quantum mechanics, in quantum theory. For the reason that will be clear, that we will discuss next week. So any physical quantity is given by a Hermitian matrix. So that's very important. So that was 4. The I guess the last one, we are running out of time. So the last point for today is that matrices can represent transformations of vectors. So matrices can represent transformations of vectors. That's obvious, but let us exemplify this point with some example with the previous matrix. So it was 1 plus 2i, 1 minus 2i, and 2. Just some arbitrary matrix. And when I multiply this matrix by the vector, let's take 0 vector, 1, 0, right? So what I would get? So I need to take the product of 1 times 1 is equal to 1. Then this number by 0 is equal to 0, so plus 0. And for the second one is 1 minus 2i times 1 is 1 minus 2i, and 2 times 0 is 0. So this is the new vector, 1 and 1 minus 2i. So we, in other words, right, so we had a vector, this plus a 0 cat vector. We multiplied this vector by a matrix, and we obtained another matrix. And that means that we can use matrices to represent transformations of vectors. And this is pretty important point, because in quantum, as I already said or mentioned, the state of a quantum system is given by vector, and everything we do, whatever we do with the vector, with the state of the quantum system, will be given by a matrix, and matrix of specific property and specific I mean, it gets a specific name, but we will discuss that in next week. So I think this is a good time to stop recording, and then we can discuss, I mean, if you have any questions. So thank you.